Hello everyone, my name is Eugene Kang and this is lab3 Black Hole and Orbits for Physics 2211. So the purpose for this lab is to first find the mass of a theoretical black hole using a computational model of Newton's second law along with centripetal and gravitational forces, and then second, to achieve a computational model of an orbit of a spaceship around a moon and planet using Newton's second law and again centripetal and gravitational force. So these computational models are going to be created using GlowScript, and the main relevant physics principles include Newton's second law, gravitational force, and centripetal force. The results of the calculated mass of the black hole came out to about 1.32 times 10 to the power of 34 in kilograms, and one possible initial velocity for the spaceship came out to be this vector right here, 1.44 and 3.93, both multiplied by 10 to the power of 4 in meters per second. So before we go into the data, let's define some of these physics principles, starting with Newton's second law. This law states that the net force acting on an object is equal to its change in momentum divided by a certain time period. Using this law, we can derive an equation known as the velocity update formula, shown here. And then we can use that equation to derive the position update formula, which is shown here. These equations can be used to predict the motion and position of a given object after a certain time period. Next, we have gravitational force, which is calculated using this equation right here, using these variables, which will let us calculate the attractive force between objects. Then we have the equation for centripetal force, mv squared over r. This tells us how strong the force keeping a given object in an orbit is. The procedure for this lab is as follows. For step 1, we have to first define the system as a star and the surroundings as the black hole. Then we have to create a computational model of the star's orbit using GlowScript and the code template for the step. Then we have to calculate the mass of the black hole for each time interval during the star's orbit. Then we have to find the average calculated mass over all those time intervals. For step 2, first we have to define the system as a spaceship and the surroundings as the moon and planet. Then we create a computational model of the spaceship's orbit using GlowScript and the code template for this step. Then we have to find an appropriate initial velocity for the spaceship for it to orbit both the moon and the planet through trial and error. So here's the video of the star orbiting the black hole. The orange arrow is the net force on the star, the magenta represents the parallel component, and the blue represents the perpendicular component. So as you can see, for each time step, we calculate the net force and then the parallel and perpendicular components. Then, by using the gravitational force equation, we find a calculated mass for the black hole for each time step. Then, we want to take all of the calculated masses of the black holes for each time steps, and then take the average of them to find a more accurate approximation for the mass of the black hole, which is this number circled in red right here in kilograms. So moving on to step 2, I was unable to achieve a figure 8 orbit, but I was able to get the spaceship to orbit both the planet and the moon as seen here. So in step 2, we start by calculating the net force of the moon and the net force of the spaceship for each time step. We can then use these numbers to predict the motion of both objects using our velocity and position update formulas. After that, it's a matter of trial and error for finding out what the ship's velocity should be, constantly inputting a velocity for each x and y component, running the code, and then tweaking the numbers again to get a better orbit. So what were some sources of error that affected our results? The first is rounding errors. Data values from GlowScript were rounded, such as the calculated outputs of the position and velocity vectors, which altered the results from its true values and explains why we see variation in the calculated mass for each time step in part 1. Then for step 2, the main source of error was our use of the trial and error method. This method didn't really guarantee that we would be able to find an ideal orbit path, just that we would eventually arrive to a velocity vector that was good enough and led to the spaceship not crashing into anything. So now for some further questions, starting with how is net force and its parallel and perpendicular components different from the rate of change of momentum and its components? Well, the answer is that mathematically, they're the same thing and are equal to each other. The only difference really lies in how to calculate both of them. For rate of change of momentum, you would just need to know the change in velocity of a system. But for net force, you would need to know about all the forces that act on the system, which gets more and more complicated to calculate as more and more forces are being applied. For another further question, let's look at a hypothetical. We have a system with a black hole, a star, a planet, and a moon. If we wanted to predict the motion of the entire system, we would have to go in and calculate the net forces acting on every single object for each time step in order to predict their orbits. In order to find out if there are any dominant interactions in the system, we would have to know their relative distances to say for sure, but it's safe to assume that the black hole would be what the rest of the objects orbit around due to its significantly higher mass. That was the end of this lab report. Thank you for your attention.